Greetings. My name is Mike Levis, and I'm an instructor with the Mount Hood Ski Patrol Avalanche Program. So far, we have covered weather and snowpack. In this video, we will cover the third leg of the AVI triangle, terrain. Some of what we're going to touch on today will be a brief review of topics covered in Avalanche Level 1. Our main focus will be on how terrain affects snowpack stability and local weather, as well as an introduction to a terrain exposure risk management tool developed by the Canadian Avalanche Association. Let's start with a discussion of terrain-snowpack interactions. What does this mean? Terrain is fixed. It doesn't change with time of day or with the season of the year. And more importantly, we can choose our terrain based on the weather and snowpack conditions to manage risk. So the key question really is, how does terrain increase or decrease snowpack stability and avalanche risk? These are the key questions we'll always need to keep in mind. Is the terrain capable of producing an avalanche? If an avalanche occurs, what are the consequences? Are there any terrain features that give us clues to avalanche risk? As we mentioned previously, we can often choose terrain to minimize risk. The answers to the above questions for each of our terrain options should allow us to make decisions that reduce our exposure to avalanche hazards. This should look familiar to everyone. The sweet spot for avalanche activity is usually said to be in the 30 to 45 degrees slope angle range. The thinking here is that below 30 degrees, there is not enough gravitational force to overcome friction and slide. Above 45 degrees, the snow sloughs off and slab formation is difficult. This is a simple, easy-to-use rule of thumb that we can use to avoid the most sensitive terrain in high avalanche risk conditions. A key point with this rule of thumb is that you need to accurately measure slope angle. Guesstimates are notoriously inaccurate. You need to use a slope measurement tool like one of these shown here to get an accurate measurement. However, let's dig into slope angle a little more deeply. As it turns out, slope angle and likelihood of slide depend on the nature of the avalanche risk we're dealing with. In this slide and the next couple of slides, we will review how the sweet spot for avalanche release varies with avalanche hazard. Let's start with loose, dry snow avalanches. These typically require higher angle, 40 degrees or more, to initiate release. As we mentioned previously, these will typically release at a single point and expand as they move downhill. Storm slab and wind slab more closely fit the traditional model, with slab release in the 35 to 45 degree range. Wet slab and loose wet avalanches can occur at significantly shallower angles, typically in the 25 to 30 degree range. Loose wet avalanches have been documented on slopes as low as 20 degree slope angle. This is because the higher water content increases snow density, reduces bonding between crystals, and therefore has lower frictional force and greater downslope component of gravitational force to initiate a slide. Cornice fall is really independent of slope angle. Cornice release can result in a very rapid extreme loading on the snowpack and result in release over a very wide range of slope angles. Persistent slabs and deep persistent slabs can occur over a wide range of slope angles, anywhere from 20 to 45 degrees. Slides are very dependent on the weak layer characteristics, the depth of the weak layer, and the nature of the trigger. Deep persistent avalanches tend to require steeper slopes. Glide avalanches result from water at an interface in the snowpack, typically the ground, reducing friction to a point that a tensile crack is created upslope. This tensile crack usually starts at the ground and propagates upward to the snow surface. This release increases the glide speed of the slab downhill. Note, glide cracks can form and be in place for days or weeks before the slab actually accelerates downhill. Glide avalanches tend to occur on slopes in the 30 to 40 degree range. So as you can see from the above, there is not one simple number for slope angle. It depends on the nature of the avalanche risk we are concerned about. When we talk about slope angle, what exactly are we measuring? On a slope scale, there will be a wide variety of topological features, such as the concavities and convexities shown on this slide. They will vary in size and degree. Generally, concavities tend to be more stable due to compressive nature of the forces, while convexities will have higher stresses and be less stable. But on a slope scale, we would expect to find a large variation of slope angles based on the topological features, and therefore a wide variation in sensitivity to avalanche release across a slope. When we measure slope angle, we are really only measuring the average slope angle with a lot of variability across the slope. This slide shows some interesting data from a research study exploring spatial variability of avalanche release. The picture shows a slope where many root block test pits were constructed and tested to failure. As you can see, there's a lot of variability across the slope. Larger numbers indicate more stable locations on the slope, whereas smaller numbers indicate locations that failed quite quickly. For example, an RB root block failure level 2 is a failure that occurs as soon as the skier gently steps down on the block. So what does this mean for us? It says that even when stability test data from a pit indicates a stable slope, it is only data at one point on the slope, and other portions of the slope may be much less stable. When combined with small variations in slope angle across a slope, there will be a wide variation on avalanche release sensitivity. Terrain traps are another terrain feature to be aware of. This was covered extensively in avalanche level 1, so we're not going to discuss it in any depth here. Just remember that terrain traps are consequence magnifiers. They make shallow burials into deep burials with all the bad things that implies. Avoid them whenever possible. So you're traveling through avalanche terrain and you're trying to manage your exposure in the event of a slide. One question you might ask is how far, that is what distance, would the run out of a slide extend from the base of the slope? One way to assess this is to measure the alpha angle of the slope. The alpha angle is defined as the angle from the horizontal of the line from the crown face to the greatest expecting run out of a potential slide. This is usually calculated from historical data for the mountain of interest. If no historical data is available, it can be calculated using avalanche slide evidence on the mountain. In the figure, the skier is measuring the alpha angle of the line from the crown face to his location. If this angle is greater than the alpha angle for that region, then the skier is still exposed to run out in the event of a slide. If the angle measured is less than the alpha angle for the region, then the skier is outside the run out expected from a slide. Here are several more examples of alpha angle. Note that alpha angle is not slope angle. The difference between slope angle and alpha angle is a measure of exposure to a slide. As the slope angle decreases and approaches the alpha angle, the risk from avalanche runout is reduced. In this photo, the person at point X is clearly at risk since the slope angle is much greater than the alpha angle. Note that in this case, the alpha angle was measured using actual avalanche data since there was a recent slide. Let's shift gears and talk about terrain-weather interactions. I'm sure you've all heard comments like mountains create their own weather, but what does this really mean? Much of this will be a review of material from avalanche level 1, so we'll go through this quickly. The simplest form of weather-terrain interaction is related to aspect ratio and the impact of solar radiation. Solar radiation, as we learned in previous modules, can have a big impact on snowpack stability. Duration of solar exposure during the day and variations in duration throughout the season can drastically change the snowpack structure and avalanche risk profile. Of all the terrain weather interactions, wind probably has the greatest effect. The terrain shapes and steers the wind. Wind is compressed by the terrain, which has the effect of increasing wind velocity. These terrain features steer the wind and therefore determine where snow will be redeposited. Wind redistribution of snow can quickly increase loading on leeward slopes, greatly increasing slope instability and the likelihood of a slide. This is a major factor for avalanche risk on Mount Hood. Ridges are terrain features that interact with the wind to sculpt the snowpack. The wind approaches the ridge on the windward side and in the process removes snow. The snow is then deposited on the leeward side of the ridge. The wind flow is compressed as it passes the ridge, accelerating the wind. On the leeward side, pressure is reduced, wind speed decreases, and snow is deposited. The steeper the ridge, the greater this acceleration-deceleration effect. This picture shows visually the effect of the snow redeposition by the wind, in this case due to a man-made ridge, a roof. Notice the difference in snow depth on the windward and leeward sides of the ridge. On the windward side of the ridge, the snow will be scoured away. Snow that remains will be pulverized crystals in a highly compacted slab. The effect of this scouring and pulverizing is a very stable slab that generally is not prone to sliding. Snow that is removed from the windward side is redeposited on the leeward side of the wind as the wind decelerates. The deceleration and redeposition creates cornices, snow pillows, and wind slabs. The redeposited snow rapidly increases loading and is more prone to avalanche release. So far, we've discussed wind loading primarily across a ridgeline. However, wind can also flow across a slope, resulting in redeposition of snow across high points on the slope. As shown in this picture, wind flowing along the slope redeposits snow across localized high points, resulting in cross-loading on the slope. This cross-loading will create areas on the slope that have increased loading and are more susceptible to slides. Valleys offer the potential for inversion layers, where warm air is trapped over colder air. The colder air trapped in the valley can also result in surface hoar formation, which can form a weak layer when buried. One key element of terrain assessment is signs of previous avalanche events. Avalanches tend to slide in the same areas repeatedly, so past signs of avalanches are good indicators of where future avalanches will occur. Look for slide paths, broken trees, and clear areas on slopes where vegetation has been removed as indicators of past avalanches, and be alert for future slides in these same areas. Vegetation can modify the effects of weather on terrain. Wind can be obstructed or steered, affecting where wind loading occurs. Vegetation can provide shade to inhibit radiation effects. Vegetation can facilitate surface hoar formation. The key point to remember in all this is that vegetation is not static. Trees grow or are removed through logging, for example. Vegetative effects will change year to year. As discussed in Level 1, trees can act as anchors or can act as stress points where release can be initiated. Generally, the farther apart the trees, the less effective as anchors and the more likely to be stress points. So the key point in all of this is terrain consequences. How can terrain contribute to risk as we travel? Look at these pictures on this slide and ask yourself, what sort of terrain hazards do you see here? Take a moment to pause the video and think about this and come up with some answers. We'll discuss more in our classroom breakout session. It's important to get a sense for terrain consequences before we leave home. Route planning using tools such as Caltopa or Gaia with a slope angle layer should allow you to identify high angle slopes, terrain traps, and those sort of terrain hazards during your desktop route planning. In our classroom session, we're going to introduce you to a tool developed by the Canadian Avalanche Association to assess and describe terrain exposure. This will allow you to quantify the terrain hazards to others in your group. So this brings us to the end of our terrain module. Keep in mind the 3 questions we stated in the beginning. Is the terrain capable of producing an avalanche? What terrain features are there to indicate avalanche activity? How does the terrain affect the consequences if I'm caught in a slide? The basic rule of route selection is stated at the bottom of the slide. Avoid steep slopes when the snow is unstable. Do not enter them and do not cross below them. Be obsessed with consequences. So the bottom line is we always want to try and match the terrain to the conditions in the snowpack and the conditions we find on the mountain that particular day. Thank you for your time.